I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll briefly discuss about Bayesian linear regression in AIML. The Bayesian linear regression offers a probabilistic framework for modeling relationship, providing uncertainty estimates and handling small data sets effectively. It's valuable in AI for informed decision making and quantifying uncertainty. This approach is particularly useful in applications like robotics, finance, and healthcare. By incorporating prior knowledge and updating it with the new data, Bayesian linear regression enables robust modeling. It also facilitates model comparison and selection through Bayesian model evidence. Overall, it's a powerful tool for AI and machine learning. We'll see one by one. First, we should know why is Bayesian linear regression. So Bayesian linear regression, this we are calling it as BLR. BLR means Bayesian linear regression. This BLR is a probabilistic alternative to traditional linear regression. Instead of estimating fixed point values for the model parameters such as weights and bias, the Bayesian linear regression BLR models these parameters as probability distributions. This means the model captures uncertainty about the parameters based on both prior knowledge and observed data. Predictions in BLR are not just a single value but all are expressed as probability distributions over possible outcomes and allowing the model to express confidence and uncertainty. This becomes especially useful, this BLR, in domains where data is noisy and limited, such as healthcare or autonomous systems, where overconfident predictions can be risky. Why BLR is important in AL? This is all you should know. In real world machine learning and artificial intelligence tasks, data is often noisy, sparse, or uncertain. Bayesian linear regression is important in AML because it addresses these issues directly. Traditional models provide only a point estimates with no insight into how confident the model is in its prediction. But PLR, however, naturally incorporates uncertainty by providing a full predictive distribution. This allows models to make risk aware decisions, especially in sensitive applications like medical diagnosis or autonomous vehicles. By considering both prior beliefs and data, BLR provides robust, interpretable, and principled results, which is why it's increasingly used in modern AI ML pipelines. How it works, the conceptual view will see. Bayesian linear regression begins by assuming a prior belief about model parameters, typically that the weight follow a Gaussian distribution centered around 0. Once the data is observed, the likelihood of the data given the parameter is computed. Bayes' theorem is then applied to update the prior belief into posterior distribution, which incorporates both the prior knowledge and the observed evidence. This posterior distribution is then used for making predictions on new data points. Instead of single prediction, the model outputs a distribution representing a range of plausible outcomes and their associated probabilities. This approach allows the model to adopt its uncertainty based on the amount and quality of data available. Next, we'll see how the Bayesian linear regression, that is BLR, in ML pipeline stages. Bayesian linear regression plays a unique role across various stages of machine learning pipeline. During the modeling stage, BLR is particularly effective for data sets with high noisy noisy data or when data is limited. During training, instead of optimizing parameters via loss function, what it will do is the BLR updates the probability distribution of weights. In the prediction stage, the output includes both mean prediction and uncertainty estimates, allowing for more informed decision making. BLR also inherently incorporates regularization through the prior distribution on the weights, helping to avoid overfitting without the need for manually tuning regularization parameters. This makes BLR a robust and efficient option in many machine learning workflows. Next, active learning and optimization. One of the most powerful application of Bayesian linear regression is in active learning. BLR can be used to select the next data point to label based on the areas of highest uncertainty, making the learning process more efficient. In Bayesian optimization, BLR is used to model the objective function and guide the search for optimal hyperparameters by balancing exploration, trying uncertain areas, and exploitation, focusing on promising areas. This is particularly useful in situations where training models is computationally expensive, such as tuning neural networks or performing architecture searches. Next, we will move on to the AI applications using BLR, Bayesian linear regression. The Bayesian linear regression is widely used across multiple AI domains where uncertainty quantification is critical. In computer vision, it helps in tasks like image segmentation by modeling pixel-wise uncertainties. In natural language processing, BLR can predict sentiment or topic probabilities with associated confidence levels. In healthcare, AI, it's used to predict patient risk score while accounting for the confidence in those predictions. In finance, if you are coming into the finance, BLR models helps forecast market trends with credible intervals, offering better risk assessment. In robotics, it helps predict trajectories or object positions with an understanding of the uncertainty, allowing safer navigation and interaction in dynamic environments. Next, if you are taking the example, self-driving car, how the ordinary network works and BLR, traditional and BLR works. Consider a self-driving car that needs to predict in its future position on the road. A traditional regression model would provide a single predicted location for the next 5 seconds. However, this point estimate could be risky if the model is uncertain due to environmental changes or limited data. A Bayesian model, on the other hand, would not only predict the most likely position but also a range. Example with 95% confidence where the car is likely to be. This probabilistic prediction enables the autonomous system to plan safer paths, slow down if the uncertainty is higher, and trigger fallback strategies, ensuring safety and reliability. Coming into the summary, why use BLR in AML? Everyone should know it of. Bayesian linear regression is a powerful modeling technique that offers several advantages over traditional models, particularly in AI machine learning applications. It quantifies uncertainty in predictions, which is vital for making safe and informed decisions. BLR also incorporates natural regularization. So this is very important application through priors, which helps avoid overfitting, especially in low data scenarios. It is robust, interpretable, and capable of guiding optimization and active learning process effectively. These strength makes it an essential tool for modern AML systems that demand not only accuracy but also reliability and transparency. Hope everyone understood about what is BLR, what is the difference between the traditional models and the probabilistic BLR. The remaining things we'll discuss in the next lecture. Thank